Okay, um, so we're going to start by talking about the operating system services and basically how do we control the operating systems, which means what control functionalities we need to create inside the operating system so it can be controlled by the programmers, right? This is our main goal, okay? So as we said last time, there are two main point of views from which we're looking at the operating system. One of them is from the user standpoint and the other one is from the programmer standpoint. So based on this, we're having, as you can see, three types of interfaces with which we can interact with the system, right? So the first one is the command line interface. So how many of you have used command line interface to interact with the system? Okay, anyone on the back? Okay, nice. Yes, yeah, exactly. So on Windows, it is the command prompt. On MacBook, there is also a window. Actually, on the Macs, we're using Linux-based commands. Okay, and the Windows commands, they're usually completely different with some exceptions. Okay, this is just because of the core structure, how those systems are built. And of course, with the continuation of our class, I will also show you some examples of those commands, how you can use the terminal. Actually, the terminal, using the terminal, this is the quickest way to interact with the system, because you can imagine if you just click on things, you're way slower in running operations. Obviously, the next type is graphical user interface, which is what we'll use. Simply clicking on some things on our monitor, and by this we are actually activating some operations. And the final way is batch, which means that, let's say, we're having files with some scripts, and those scripts are actually performing system calls and are doing some activities inside our system. Okay, so those are the three main ways to interact with the system. Now let's see how an operating system structure looks like. Okay, so last time we just saw a simple picture that we have hardware, operating system, user applications, right? So now we have some more things here. So obviously above the hardware we have the operating system, and right here we have a few modules, as you can see. So first of all, you have the services, and those are the services that the operating system performs. And we're going to talk about those as well. Then we have, on the next level, we have the system calls, which are the calls that interact with those services. And on the upper level, we have the user interfaces. Okay, so the user interfaces can perform system calls to access those functions right here, to access the hardware of the computer. Okay, and finally, here are the user and the system programs. Okay, so either the user can use those interfaces, or programs can also use interfaces, right? If you have some script, the script can also interface automatically even with the GUI we can interface automatically, right? So for example, if you write a bash script in Linux, okay, there you can add sequence of things that you would normally write in the terminal, and those will be executed automatically. If you're using frameworks, for example, for web testing, let's say Playwright, Selenium, have you heard of those? Yeah, Selenium, you heard, yeah? So, for example, those tools, they are going to interact with the interface, so with what we see on the screen. And they're actually going to use, and in this case, test the user interface if it works properly. So, this is why I'm saying either the user or programs can use the interfaces. Okay. Now let's see what operations are actually possible for the operating system, or what operations we can call using system calls, which means what the kernel can actually do. And this is not always the case. Sometimes we purposely want to make the kernel with as less functionality as possible when we use microkernels, but we're going to talk about this a little bit later. Okay, so you can see that first of all we can perform some tasks for program execution. Okay, loading programs into the memory, run a program, execute a program, and so on. So you need to point the location of the program and do the system call to execute this program into your system, right? We can do output operations. Okay, so sometimes a program may require for you to use a monitor, external hard drive, keyboard, and so on. So you need the operating system to assess those input-output devices, and you really want the control of those devices to be dedicated to the operating system, not outside of it, because otherwise somebody can just send you some virus, you're not protected, and then they can get control to the input-output services. Okay, obviously the operating system can manipulate the file system, right? So read, write, execute files, and so on. Also you can create, for example, directories. So every time when you create a directory on your device, whether you use terminal with, for example, from the terminal in Linux, you can write mkdir and then the name of the directory that you want to create. Or you, for example, on Windows, you can just right-click and select new directory. This is exactly the same. So when you do that, you're sending a system call to the kernel, and then the kernel runs the system call and creates a folder. Okay? Okay. Then communications. So obviously, we also spoke about this last time. Programs can interact with each other, right? So when you run one program, this program might require the services of another one. Okay? So let's say you download some let's say camera application on your computer, and maybe this camera application wants to access another program that actually controls your camera, for example. Okay, and finally, of course, very important, the operating system also needs to have system calls that are doing error detections. So for example, if the operating system fails, we'll need to have some dump file, right, where we're going to see all the information about the failure, and so on. So we need functionalities for detecting errors. Okay, so other things that the system calls can do is, for example, resource allocation. This is pretty much one of the most important tasks of the operating system. So how much CPU cycles are we going to allocate? What part of the main memory? Where are we going to put our program? Okay, where we're going to store our files, right? Those are all operations of the operating system. Accounting. How do we keep track on, for example, how many times a user have been logged in? How we keep track about some system information that we might need later to analyze the system if it performs good. Obviously, we need accounting. Okay, and finally, as well, we need security and protection, which is pretty much how we protect ourselves from viruses, malicious activity, and so on. Okay, so now we're going to focus about the interfaces with which we interact with our device. Yes? So when we do a system call, the operating system what?
Does it always execute on behalf of the user, or it just lets the user send the directly to the kernel?
I see what you mean. So you will see later that firstly we have an interface between the user and the operating system. Okay, and for example, when we want to execute a system call from the user, so we have a user mode, if you remember from the last lecture, and a system mode. Okay, so the system switches from user mode to system mode, and this is when we execute the system call inside the kernel. Once system call is executed, then we switch back to user mode. Okay, and also specifically how the system calls get executed, we'll see a little bit later. You'll see how this is protected and how we're using a specific interface with API. Okay, but I'm gonna get to this and explain a little bit more in the next slides. Okay, is that answering your question? Okay. Okay, so as I said, we're going to talk firstly about the command line interface. So normally, there are different types of command line interfaces, as some of you might know, and those are called shells. Okay, so shell is your command prompt when you write your commands. If you want to create a shell script, this means that you write a program that writes automatically shell commands and execute them one after another. Okay, so they have different names, as I said, depending on the different devices that you use. Okay, so an important thing is, of course, that from the shell we can easily access the kernel. So we have some commands that are specific for any operating system, and by writing those commands, we can then perform system calls and, of course, create files, folders, execute things, allocate resources, and so on. This is why I'm saying we have way more control over our system when using the terminal. Okay, so this is an example of how you can actually write something in the terminal, right? This is actually pretty dated image, but as you can see here, you can write something as user. For example, if you write the pwd command, this is going to list all of the directories, or I think it was all, yeah, it's going to list the current directory that you're in, for example. And actually, I think it's easier if I just show you on my terminal. We can just write a few commands so you can see. So, okay, so this is a typical Mac terminal, right? So, for example, if I want to create a directory, as I said, I can just do mkdir folder 1, as you can see. And then if I do ls, you can see that we created folder 1. Okay, so as you can see from the terminal, it's way more simple. If I do the command that we just saw over there, so if I do pwd, okay, I can see the current directory that I'm in. If I write ps, for example, I can see all the processes that are currently running in my system, which, as you can see, are not many. Of course, you can also try on your computers. So even if you use Windows, the commands are just going to be slightly different. You can, of course, Google them. But for example, let's say a command that is quite common for both Windows and Mac. For example, this is the command cd, right? If you want to enter to a folder. So if I do cd, what was it, folder 1, okay, you can see that I can enter inside the folder. So those people, for example, that were in the AI class, I think you were there, right? You saw that last time I was just using the terminal to write commands because it is way more simple, right? So you can create, let's say, virtual environment in Python. You can access all the libraries that are on your device. Okay. For example, let's say if I do read let's see, or let's say if I do the echo, okay, and then I write enter your name, okay, and then I write Martin, is it going to work? Oh no. Okay. How about if I do A? Okay, let's see if this terminal actually has a touch command. So if I do touch, okay, and then if I do file name dot txt, okay, and if I do ls, you can see that now I created one file right here. And if I do, for example, chmod, and then the name of the file, oh, I think it was -m. Let's see. Oh, actually, here's what we're gonna do. So if I do -l, okay, so now what we did here, for example, I create a file, right? And after that, when I do ls-l, for example, on Linux, what you can see is your files, but also you can see additional information. For example, here you can see the permissions. So you can see that most of the users can only read the file, okay? Only the user that created the file can read and write to that file, okay? So, for example, if I add now chmod plus x, okay, and I do ls-l, you can see that now I have this x here, which means that now I can also execute the file in the system, okay? So I'm doing this example, it's really a very brief example, but I just want you to see how easy it is to have to create and really have more controls over your system. So those are just like a very small amount of commands. Of course, if some of you have been working with Linux at your jobs, you probably use those commands. They are pretty basic. But yes, you have way more control. All right. Any questions about this? No questions? Okay. All right. So we're not going to talk too much about user interfaces because I would say from my point of view, they're, if you think about operating system, they're not that interesting as the command line interface. Okay. Obviously, we're having two types, touch screen and the one that we can interact with keyboard and mouse. And of course, depending on what user interface we have, then of course we will need to have slight changes inside our operating system. However, for example, in the Android, I guess some of you are using Android phones, right? So in the Android operating system, when they initially built it, they used the Linux kernel for that purpose, okay? And then Google just modified the Linux kernel, and then they continued building their own system, okay? I just want you to see that when a new technology is developed, obviously you need some baseline, something that is already being used, and then you can modify it and add more features, okay? Okay, so these days, most of the operating systems are written in C or C++ as a core language, okay? Some of them, mainly in the past, have also been written in assembly language, and later we're going to see what is the difference between an assembly language and C or C++. But now let's focus on the system calls, okay? So, first of all, who of you knows what is an API? A pretty simple. I couldn't hear. Okay, so let's say, and I know we talked about APIs last time, but now I'm going to ask you an additional question. So, when we use the API, okay, what's been hidden from the user? So we use the API to hide something, right? What do we want to hide? Maybe more detail. The what?
Basically, the code.
Yeah. Okay.
I was gonna say that, like the program instructions.
Yes. Okay. So yeah. when we use API, we want to hide the code that is under the API. We don't want anyone to have access to it. We don't want anyone to read it for two reasons. First reason is if somebody can write into that code, that's not good. We don't want our code to be changed. We just want it to work as it is. And the second reason, we might not want somebody to see our code even though they don't edit it, because we just want the program to be our own, and we don't want somebody to do exactly the same thing like us, right? We want to keep our programs private. The same thing is inside operating systems, okay? So I just list you a few types of APIs that are used in today's operating systems, okay? And the API, in terms of operating system, is what stays between the system calls, okay, and the users, okay, or the user interfaces. So the idea is that we never actually see how the system is implemented, what is the code in the system. The only thing our programs care about and the users care about is to send an input and get some output, okay? For example, if you use the open function, right, the input is going to be the name of the file, and the output is going to be your file opened. Yes?
The API is almost kind of like the wall between the user and the...
Yes. Yeah, exactly. What you expect is for you just to send some, so usually you send the function name with some input to that function, right? And you're going to get the output of that function without knowing what's happening inside the function, right? This is the idea. So some of the most popular APIs for Windows, for example, is the Win32 API. With this API, by the way, because Windows now owns so many applications, for example, they own also PowerPoint, Word, Excel, so many of those. So with this API, not only you can do system calls to the kernel, but also you can do automatic commands to the Windows applications, right? So for example, you can write a code that can automatically create presentations and design them based on certain data that the user adds. So then the user doesn't need to build a presentation slide by slide, okay? Just an example. The POSIX API is the one that is used for Unix, Linux, and Mac OS, okay? And this API connects with the Linux kernel, and this is how we execute commands. So right now, when we saw the command line interface, this is the API to which my commands were sent, and then I just received the output of those commands. And obviously for Java, if some of you are familiar with Java, okay, then we're using the Java API to interact with Java functions or commands, okay? So let's take an example, okay? Let's say that what we want to do is to create two files, and we want to copy the contents of one of the files into the other file, okay? Pretty simple. So what system calls do we need to do? You can see that for this simple operation, we need to do a lot of system calls, and they're all listed here, right? So you should imagine that actually this is true for most of the computer science subjects, but most of the time you're going to just learn the mechanism on how something is done, and you should imagine that this mechanism is implemented in thousands and millions on your device. What I'm trying to say is that if for this simple operation you use so many system calls, you can see that on operating system there are thousands of system calls happening every minute, okay, even every second. So that's important to understand. So let's see the system calls that we need here, okay? So first of all, we need to acquire the input file name, right? Then we need to write some prompt on the screen, right? So the user writes prompt, okay? And we're acquiring the name of the file. Now, we accept the input, so we accept the command for let's say creating the file, okay? Then we do exactly the same with the output file. Okay, once the files are created, okay, we open the input file, which is another system call, okay? And if the file doesn't exist for some reason, we need another system call to abort the process, okay? So we're going to get an exception, and this exception will be handled with another system call, right? So if it doesn't exist, of course, after that, let's say we might be able to create it. Like if your system is designed, if you search for a file that doesn't exist, to create it immediately, which no system is designed in this way, but you can implement, it's going to be fairly easy. Okay. So once we reach a stage where we want to copy the characters from this file to the other one, obviously we're going to start a loop, okay, and we're going to read every line from the input file, which is another system call, and we're going to write it to the output file, which is another system call. Okay. Of course, this is going to appear for you to happen instantly, but I just want to show you how many system calls and operations are just happening in the background. All right, so here you can see an example of how the API is implemented, okay? So what do we see here? What is that in C? What is that line of code? So that's obviously a function, right? So the API, as you can see, is implemented by a function. Now, for example, if you want to read something, okay, so we use the command read to read some file, let's say, okay, to read the content of some file. What is going to happen? We're going to use the API to access this function right here, okay? So this one is going to be the return value, so what we expect to get out of this function, okay? And those are the parameters that we expect to pass to this function, okay? So first of all, this one is the file descriptor we want to read, okay? So this is going to point to the file that we want to read. And also, here we have a buffer where we're going to read the data into. So this means that, for example, if there is information in the file, in order for this information to be displayed, obviously you need to create some buffer in the memory, some space, in order for this information to be displayed to you, okay? So you pass those parameters, and then you get, obviously, the file that you want to see, okay? Any questions? Okay, so this is exactly related to your question that you asked earlier on, okay? So as you can see, the system call interface, which is where we implement the API, okay, is exactly between the kernel mode and the user mode. So let's say if I want to open a file, okay, I run the open function, and then what happens? We launch the API, okay, and then based on this name, what we want to do, we're going in a table that each name has a number or an address that points to that specific function. So once we run the function, we go here to this table and we're like, okay, this is the address of the open function, okay? Then we point to the specific address, and here is where the open function is, okay? So we execute the system call, and once the system call returns something, we return it back to the interface, and our application from there can then get the output of that function. Okay, so as you can see, there are many types of system calls. Some of them we talked about, some of them we haven't. Okay, so obviously we can create processes, we can end or abort a program, we can execute a program, sometimes, especially when we interact between two programs, one program wants to wait for the other one. So we can do a system call also for waiting, right? We can wait some time. Also, we can wait for some event to happen. Let's say you run a program and then you wait until you get some certain parameters. Once you get them, then you can execute the next program, and so on. You can see that we can also dump memory and so on. So this is in terms of process control. Okay, so those are the system calls that we can do for file management. So we can open, read, write files. For device management, we can request a device resource. We can again read and write into the devices. Okay, we can get some information from the system like date and time, some system data. In communications, we can create and delete communication between different processes, right? So two processes are normally communicating via messages. So there is a protocol that defines some certain structure of a message. Both processes understand the same protocol, and this is how they communicate. So with the communication system calls, we can create and pass messages from one process to another. Okay? So I put this table here if you want to use whether Linux, which is Unix based, right, or Windows. So here, for example, you can really see which Windows command or which Windows system call to which Linux system call is similar. Okay, so you can use that, and here also I divided them into different operations. Okay, so you can see for process control, file manipulation, and so on. You can try those at your own pace, okay, and see if they work on your device. Okay.
It's making me realize that Windows is a lot more verbose.
Yes, it's true. It's true. My personal opinion. How many of you used Linux terminal, like Linux commands?
A little bit
A little bit? Okay, have you used? A little bit? Okay,
for an assignment.
for an assignment. Okay, good. Anyone else that have used? You used Linux terminal? Okay. What's your opinion for Linux terminal? He, okay. Have you?
It's like a secure and
Yes. So, is there anyone that have used both Windows terminal for a project and Linux terminal for a project? Both of those.
So it's
Okay. So,
strange because I would have thought I did that first and then.
yes. So, here's the thing. My personal opinion, and I've been using for many years Linux terminal. Okay. I've also used Windows terminal. So, most of the companies that are, for example, having virtual machines and so on, and are developing software, especially if they're using, for example, embedded systems, you know that you need to connect system to a terminal, connect to the system, and so on. Most of the companies are going to use Linux. Okay, so if you're thinking on which command should I learn, Windows or Linux, Linux is way better choice, just because everybody is using it. The reason for that, there are a few reasons. First, the first one, it is free, it's open source. Second one, commands get executed way faster than Windows. Third reason, commands are way shorter, okay, and it's way easier to execute bash scripts and create all of that from the terminal, okay. So, for example, I would really advise any student, including you, to start a course or to watch a video, let's say 1 or 2 hour video on how to interact with Linux terminals, just because really everybody is using it those days. And by doing that, you're going to learn how to do basic operations way faster. Okay? So this is just some suggestion from me. Okay, so I brought you here another example. So let's say in this situation, what we want to do is not for the user to write some command, but instead we want to write code that is doing some actions in our system, right? So let's take the example. So this is a typical file structure in C, right? So what happens when a command gets executed in C? How actually the programs that are higher level or that are outside the kernel are actually interacting with the kernel? And I can give you a similar example with Python, which is interpreted language, right? And here's how it works. It is actually exactly in the same way like if you would interact with the computer. Basically, all the programming languages are built by having some phrases, okay, that they define in itself that those phrases are related to specific system calls in your system. It's pretty simple. So let's say the print f command, which is printing something on in C, right? It's printing something on your screen. What it simply does, okay, from user mode where you execute the printf command, it's using the standard C library, using the API. Then we switch to kernel mode. We use the write system call. Okay, so the write system call writes something to the screen. It uses a write system call. The write system call returns wherever we want to write on the screen. Okay, sends it back to the API, which sends it back to our compiler. And this is how programs are getting executed. Exactly, yeah. Exactly. Yeah, this is how it works. So for example, let's say you have a very complicated program in C, right? And let's say, okay, you're running a program and this program interacts on the background. Sometimes what programs are going to do, for example, they're going to execute some operation and they're going to perform also the lock system call, which what is doing is locking some piece of memory, okay, or some resources on your computer in which this program is going to work. So then if there is another program that wants to use the same resources, the other program cannot use it, and the other program will have to wait. Okay, this is another system call that programs perform very often, so there is no confusion. And because imagine if two programs use the same resource, one is reading, the other one is writing, or both are writing to the same resources, then we can have an issue, right? We can have failures. So there are just so many system calls that are interpreted. That's why they are called higher level or interpreted languages, because the system calls, they are just interpreted with some simpler words that you can use in a code and write a sequence with those simpler words. So if we say that on the highest level are the programming languages, after them are the bash scripts, because in the bash scripts we write exactly the system calls that we want to perform. They are not interpreted into other words, okay? After that is the API, and after that are the actual system calls that we use, okay? Oh, okay, that's a good point. So let's say, for example, the printf, it goes directly, gets translated to a system call, okay? But for example, in many programming languages, there are, for example, libraries that are like more complex, okay? And from those libraries, you can use certain functions, right? So if you're using a function that comes from a library, for example, are you familiar with Python? More or less? Okay. So I'll give you an example with Python. So let's say if I use, let's say, an interesting framework, okay. If I use the tkinter framework, which is used to create graphical user interface applications, okay. So in the tkinter library, which I need to install in my computer, I can have different custom tkinter functions. So if I use some of those custom tkinter functions, okay, and I call them, I'm not going to get directly to a system call. Okay, what I'm going to do is from my file where I write my application, I'm going to go to the tkinter library, and then the tkinter library is going to be a function that is performing some actions to create this window because it's something custom, right? So it will go to that function, and inside this function, then I will have some commands that are calling system calls. Okay, so what I mean is that in the programming languages, if you write, let's say, a command, it might also go to another file and then to another file, and then at some point, once it reaches the source system call that needs to be sent, then it's going to be sent to the operating system. Does this make sense, more or less? It answers your question, or you meant something different?
That executable file.
Oh, yes,
That's
yes.
the one. Oh,
Yeah, it's going to do directly the system call as it is. Yeah, it's going to directly translate what you want to, what you wrote in your code to a system call, and actually it will call the system just like if you write in the terminal.
so it throws out everything, just that's what it does.
Yeah, exactly. Exactly. Okay, so now the next thing that I want to show you, okay, is how processes are executed. Okay, so there are actually two ways: single tasking and multitasking. Okay, so in the single tasking, for example, you can imagine that we have the kernel and obviously the computer interpreter. Okay, so let's say we want to execute a program. So what's going to happen is, firstly, before running the program, some space is going to get freed, right? And after this space is freed, we make sure, so those type of systems, like it was initially the MS-DOS, want to make sure that there is enough space to run the process, okay? So it allocates a space, okay? And after that, it puts the process in this space and it executes it into your operating system. Now, how it looks like multitasking. So this also means that while one process is running, okay, you cannot run another one, okay, because we already allocated memory, okay? So you cannot run another one on this memory space, okay? So you allocate it and you run the program. How the multitasking is working, you already have all the space available, okay? And what you're doing, you're just adding different processes there, okay? So here you can do multitasking, which means that while one process is running on a specific memory, you can also run another one, okay? For example, in Linux, let's say, those of you that actually used it, you know that you can run some processes on the background. So for example, if you execute some command that takes long time to execute, if you hit Control Z, you're not going to kill the program, but you're still going to be able to write something in the terminal. The terminal is not going to be halt until this process finishes, right? So it's just going to run in the background. And while it's running in the background, you cannot, the bad thing is you cannot do any inputs to that program. However, you can now from the same terminal also launch another process. And this process is also going to go on your memory, and you can go on and on until your memory is completely filled. So this is how we do multitasking, and from the Linux terminal you can do exactly that. I'm even thinking right now if there is something I can show you for a process that is going to run constantly. Let me see. Okay, we're actually going to leave this for another time. I'll create some code that I can show you how it works. So what you can do, for example, on Linux is you can create a process, okay, which is a program that executes, constantly. And after that, let's say if you want to kill this process, you can do the ps command that I showed you. You can get the process ID, and then you can write a command to also kill this process. And this is actually something very interesting. So if you are just using your user interface, and sometimes you know how you're getting like out of memory, your computer gets slow and so on. One of the things that you can do is obviously go to your task manager and stop some of the programs there, right? Okay. But also what is a very good practice is, let's say if you go to a terminal and you can check there all the processes that are actually running in your computer. Okay. Some of them might not be shown in your task manager. So once you see all of those processes, you can decide which ones you want to kill, and this is actually going to free your computer space. Okay, so from the terminal you can really see everything that is running on your computer. So that way you can really be sure that you actually killed everything and there is no process running on the background. In the same way, in the future you might need it. Let's say if you run an application on certain port and you forgot to stop this application, right? And the application runs in the background, this port is always going to be busy no matter what happens until you kill the program. So sometimes if you get some port issues, let's say this port is busy or that port is busy, you can also write a command to show you which process on which port is running, and then you can simply kill the process and the port will be free for you to use. Okay? Okay. So now we're going to switch on how operating systems are designed and implemented. Okay? So as we said before, we have user and system goals on how we want to design our systems. Of course, for us as software engineers, the system goals are way more important. Now, so once we have the system goals, how secure we want our system to be, how are we going to run the system goals. So once we have all the goals that we want to collect, the next thing that we want to do is to find some mechanisms, okay, on how to actually build those functionalities. Okay, and this is why here what we have is mechanism is how to do something. Okay, so how to perform the goals that we have for the operating system. Okay, and then once we have the mechanisms, since the operating system is something that needs to be very stable, we need to create a policy, which means what exactly is going to be done and in what order. So the policy is going to use those mechanisms in organized way so we can actually build something that is very stable. Normally when you build operating system, the very first thing after you complete that, the very first thing is going to be for you to build the different modules that are going to build this operating system. So for example, you're going to build a module which is set of files and functions on how you're going to manage the input-output devices. You're going to build a module on how you're going to manage your memory and so on. This makes it way easier for you because you don't need to do everything at once. Okay? Okay. So normally there are two ways to write operating systems. So the first one is in assembly language, okay, and the second one is in a little bit higher level language, which is C and C++. Does anyone know what is assembly language? First of all, let's get the basics. Okay.
More than one.
More than one? Okay, what else we have here?
Assembly language was, in and of itself, was not like one of the first basic languages.
Okay, yes, we're getting close. Any other ideas? Okay, so yeah, so one of the first languages we have language with the name assembly, right? It's true. But assembly languages is a group of languages that are specific to a hardware, for example, or to a chip. For example, you get an Intel processor and you have an assembly language specifically to this Intel processor, okay? Right?
It just came back to me.
Yes.
For the class.
So this is why, as you said, those are one of the first programming languages, because what's gonna happen? Yeah, no worries, come in. Because what would happen, the manufacturer, let's say Intel, is going to build a chip. This chip will be added to a hardware, right? And then the programmers will use a manual for this specific chip and write code in order to build the operating system. Okay. Now, what is the problem with that? Any ideas? It is chip specific. So let's say next time, if I want to create operating system for another chip, I have to start everything from scratch. There is no way that any piece of this code that I write is going to be able to run on any other chip. Okay? And say it again? Yeah, so this is, yeah, integrated. This is something specific language that is integrated for this specific chip. So we overcome this. Yep.
Basic or Cobalt language?
Say again?
Basic or Cobalt.
Oh, Cobalt. Yeah. So yeah, this is another example. Now, for this reason, we're actually using a little bit higher level languages, which are C and C++. We can also have applications on Perl and Python as well, or even shell scripts, but those are more interpreted languages, okay? So those don't interact, let's say, directly with the hardware. That's why it is common practice to write everything in C and C++ for operating systems. Now, an important point here is that even if I write everything with C or C++, this still doesn't mean I will be able to use this operating system into every chip. Still, for every chip, we need to make modifications to our operating system code. However, it is way easier if 99% of the operating system is written in C or C++, okay, and we just change this 1% that is the difference between the chips. We just write the functions that are giving all the information to the rest of the code, okay? So this is the idea. So still, even in C and C++, we might need to have, for example, a configuration file, right? You have configuration file with things specific to the different chips, but most of the code is always there and it's always going to be the same, which is the big advantage, and this is why we're using those languages for the operating system these days. Okay. In fact, in Linux, actually, we're having system calls in all of those languages, okay? Linux is using multi-languages, and I will show you exactly why, okay? But we might have programs in all of those languages. You always need to remember, for example, if you use Python, Python is always slower than C and C++. There is no way Python to ever be faster than them, simply because Python is one level above. C and C++, they go directly to the chip through the assembly language, while Python is one level above, okay? So you need to have some basic system characteristics running. You cannot interact directly with the hardware to use Python, okay? That's important. Okay. So now, once we have all the foundations, now I will introduce you to some basic operating system structures, okay? So you can see how they work. So we're going to talk, firstly, we're going to cover some simple structure, which is the MS-DOS. Then we're going to go to the initial structure of Unix. okay, then we're gonna cover the more modern operating systems which use a layered approach and microkernel, and actually a combination of those. So in fact, today's operating systems are pretty much some combination of layered and microkernel operating system structure. Okay, so let's see how those work. You have question, or you're just okay? Call the operating system and the operating from the operating system they call something in the hardware. Yes.
Then the kernel talks.
Yes. Yes.
That's the one essentially talking about.
Yes. Exactly. The configuration for specific chip. Exactly. Um, so, and the system calls, they're inside the kernel, right? So you imagine the whole kernel, and inside the kernel you have the specific code for the system calls. Okay, so you have the kernel. The system calls are actually something that access files inside the kernel. Okay, and above that you're having the interface with which the outside functions outside the kernel are interacting with the kernel, which means interacting with all of those files inside the kernel. And then from the kernel we go down to the hardware. Okay, but yes, as you said, for every chip we will need to have slight modification, of course. Yeah, slight modification in the kernel, but again, this is making it still way easier than writing something in assembly language. So let's say there is no standardization for chips from different manufacturers, right? So let's say it might be way easier if I write operating system for Intel that is dual core to write operating system for another version of Intel, right? So that yes, but let's say if you're using AMD and you're using Intel, there are going to be more modifications, of course, in the operating system, and the operating system will actually detect when you install it. It will detect which chip you have and will run specifically this configuration for your specific chip. Okay. Of course, there is also a way to bypass this. Of course, if you already have operating system and you create a virtual machine, you know what virtual machine is? It's pretty much a computer inside a computer. Okay. Okay, so that way, virtual machine is interpreted. So yeah.
It's like a simulated or remote controlled OS.
Yes, yes, it is exactly. It is simulated, and that's why virtual machines are way slower when you use them. Okay, no matter what happens. But you can use different operate. For example, you can use Mac OS on let's say Windows device, right? So yeah. Okay, let's see firstly the structure with MS-DOS. So you know MS-DOS it was one of the first operating systems created. And here the thing is that when the system was created, it was meant to be used on way smaller scale. Okay, it was not meant to be used while people are using internet or while multiple machines are connected together or on multiple devices and multiple chips. Okay, it's been just created, I think, for Intel 86-bit chip. Okay, and it could work only on those. So because it was not created for bigger scales, you can see that, for example, the application programs, okay, they can directly interact with the device drivers, okay? Yeah, with the ROM device, for example, the read-only memory device, okay? You can see also that, so let's say the system programs, okay, they can interact again with the MS-DOS device drivers, and the MS-DOS device drivers can also work with the read-only memory. Now, the problem here is that you can see that the application programs, they have direct access, you know, to the system programs, and also they have direct access to some of the device drivers, okay? And of course, this can introduce a lot of problems. So this means that if I have a program that want to change specific files in how we manage device drivers and how we manage the system programs, okay, then we can actually change the code of the operating system, and the operating system can easily fail, even if we don't want to. Not to talk if there is a virus, okay? So it's very easy to build a virus that is going to take down such a system, okay? So you can see that the idea for the kernel was introduced with the Unix system, okay? So here we actually had a kernel, which, as we know, is something that holds all the functionality for the operating system, okay? So here we have all the support, you know, for the CPU scheduling, for the memory management, and all this, okay? So this was really the first step on how we work with kernel. And actually, I can show you how the system looked like. Okay, so this system was working fine, but the problem is that, for example, in the kernel right here, okay, you can see all of those operations that the kernel is doing, okay, which is actually how we already described kernel, okay. We already described the kernel is doing all of those operations right here, okay. However, if we just have all the kernel implemented in one layer, okay, then it is more difficult to manage the different processes that are happening into it. It is way easier if we also subdivide those processes into different modules. Even for the sake of, let's say, if something goes wrong, just so we know in which subsystem exactly it went wrong. So this was a good approach. However, just because of the fact we have at the same level multiple processes at the kernel, it was later overcome by other operating systems. But this is pretty much what we've talked about. So obviously here you have the shells, the interpreters, and so on. Here we have the kernel, and then here we have some functions on how the kernel actually interacts with the hardware. Okay? We can say that this system had monolithic structure, so you can imagine that everything is implemented in one big block. Okay? Now the systems today, they are mainly with layered structure. Okay? So if you imagine that the user interface is the outer circle, okay, and the inner layer is the hardware, okay, then what we want to do is to build layers between the inner layer and the user interface. And we can build many layers. So what is the positive thing about it? So let's say if some system calls in the kernel are dependent on other system calls in the kernel, what we want to do is to implement those other system calls in lower layer, okay? And we slowly build functionality. So why is that good? That's good because if problem occurs while building the layers, it is way easier to detect. Let's say we have our hardware and we build layer 1, okay? We make sure that everything in layer 1 works, we debug it, we know everything is great. Then we build layer 2 and we test it. If something fails, we know that layer 1 is already debugged, so it's definitely in layer 2, right? And from there we build more and more and more, knowing that each previous layer is working completely fine. Okay? If something happens in the top layer, we can also debug the layers under it, okay, based on the functionalities on the layers below them. Okay? So that way it was way easier to detect bugs, yes.
So, but
Okay, so those layers that I'm talking about, those layers are inside the kernel. Okay? So you can imagine in the kernel you have multiple system calls, which system call is pretty much a function inside the kernel that is doing something. So,
I was thinking about like the whole operating system.
oh, okay.
The kernel
No, it's good that you ask so I can clarify it. So here I'm talking, of course, on this picture we're talking about the whole operating system, but those layers are also valid inside the kernel as well. Because even in the kernel you have system calls that are dependent on others, right? So first you're gonna make the most basic, then you're gonna make the ones that are dependent on the most basic, then you're gonna build one above them, and so on. Okay. So this is the idea with the layered approach. Okay. So another approach that was quite successful was to actually remove some of the functionalities from the kernel, but use the kernel to interact with those functionalities, so it is still secure. Okay, and the first system that was built with microkernel was called Match. Okay, let me show you how it looks like. Okay, so if we want to make our system even faster, so let's say we want our system to load fast or faster than the previous system, the easiest way to do that is to really remove some functionality from the kernel. Okay, and this functionality you can load it somewhere else on some other memory, either at the same time or while your operating system is working. But then you're going to ask me, okay, but if this is working outside the kernel, how is that secured? Because until now what we were talking about is that the kernel is like a shell that is very hard to be penetrated, right? Okay, so is that insecure? Well, there is a way to make this secure. And this way is to enable the users to interact with those modules that we put outside the kernel through the kernel. Okay, so what we're going to do is we're going to use the API of the kernel. Okay, so let's say if I have a program that wants to use my file system, okay, I can say, okay, I want my kernel just to focus on the CPU scheduling, memory management, and process communication. Okay, this is all I need from the kernel because those are the core things that my computer needs. Okay, so let's say my application is to manage the file system, okay, to read and write into files. So what I'm going to do is I'm going to implement this functionality or this module outside the kernel, but there will not be direct access to that module from nowhere. Yep. So we can, yeah, this makes it a system application, right? Usually we call it a system module, but yeah, also a system application. Something that is outside the system, which means it is in user mode. Okay, it can be accessed from user mode. So even though it can be accessed in user mode, if a program wants to access, for example, the file system, what the program needs to do is to send a message to the kernel. Then the kernel may or may not do additional system calls, for example, to allocate resources for these files to be created, right? So we're going to do a call to the kernel, and then the kernel is going to do a call to the file system. Okay, and this is how we can actually implement many modules outside the kernel. This is a very good methodology on building operating system because that way your operating system is actually going to be faster. Okay, and I will show you an example on a little bit later on how, for example, Mac OS is built, and you will see that there we're using some sort of microkernel plus other things as well. Okay, now the last basic structure of the operating system that I want to show you is operating system that has loadable kernel modules. Okay, so what we can also do is some of the kernel modules that, for example, we don't need them immediately when we start the computer, we can start them later. Okay, actually we can choose whether we want to start them later at boot time or at runtime. Okay, so that way when you boot your computer, okay, you do not load some of the modules that are inside the kernel, so that way your operating system boots faster, okay. But if you need those modules, so if you do a system call that requires those modules will be loaded, okay. That makes the operating system more lightweight, and it's also another approach that is quite successful. So you can actually see how this works here. So this is the Solaris kernel. So we have the core functionalities, okay, and then we have those loadable modules. So obviously, the scheduling and what else? So for example, the device drivers. Obviously, if we don't have certain device that is attached to our computer, we don't need those drivers loaded, right? So we can skip them until we have this device loaded. So this is the idea here. All right, so as I said, this is the Mac OS structure. And as you can see, this is some combination between the layered approach, okay, and using microkernel. So in fact, Mac OS is using the match microkernel, as you can see here, okay. This BSD layer is actually used for you to be able to interact, okay, with the kernel environment, okay. So when you write commands, they can send system calls and so on, okay. So in Mac OS, obviously you have the graphical user interface, and then you have the application environments, which are different programs with which you can write software, or software can be interpreted with those programs, okay, and from there they can create system calls to the match kernel, which again has some limited functionality comparing to what an Asian kernel was with all the operations there. So this is how Mac OS looks like.
So it's an always on its own.
So, the BSD, what if it's always on?
Like always load, it's an always of its own. BSD.
The BSD, okay. What about it?
No, I always load it. It's an always of its own. But it's using Mac OS as its micro OS.
Oh, so actually this is Mac OS. X is just a previous version of Mac OS. Is that what you meant?
Yeah, but there's an operating system called BSD.
Oh, operating system called BSD. I'm not sure. It could be, yeah. It can very much could be.
Is it the same thing or it's totally different?
No, so it might be, okay. But Mac OS, it's the operating system, okay, and the BSD, this is just a functionality that is making us able to assess command line interface, right?
Yeah, it's the different.
Sorry?
BSD OS.
Okay, so good. So maybe this type of functionality is taken specifically from this system, because as you can see, for example, the match, this is also taken from the match operating system, and the kernel is taken from there, right? So yes, BSD, this makes sense that it was from another operating system. Yeah.
It was well used for server roles, so they may have implemented parts of it.
Oh, nice. Okay, that's good. That's good. Maybe I should give this to you as a topic for a presentation or something like this. That's interesting. Yeah. Okay. So, for example, Java, obviously, this is an API that interacts with Java. Cocoa interacts with C. Okay, so this processes the C code. All right. So, iOS, this is the operating system that is run on the iPads, on the iPhones as well, right? So, this is also built based on the Mac OS kernel. Okay, so it's using similar functionality, but it is of course designed for the chips of the of the of the iPhone, of the iPad, and so on. Okay, so we're not gonna cover it too much. Obviously, in Apple, they like to rename things with like interesting names, right? So obviously, Cocoa Torch is just the C API and so on. Okay. As you can see here, we have the media services that are processing the graphics, the audio, and the video right here. Okay, and then we have the core services, which are used for cloud computing and databases. Okay, it's right here. So, as I told you early in the class, Android is actually using the Linux kernel, and then they modified it in order to be applicable for the Android phones, right? So the different companies, of course, they built different phones, and Android, as you can see, is using the Linux kernel, but it is quite similar to the iOS. Okay, so I will just show you the basic structure so you see. Okay, so as you can see here, in the bottom is the Linux kernel, okay, with all the functionalities there. Then on the top of that, you have libraries, okay. For example, WebKit, obviously to work with web application, to understand websites, to read web-based code, okay, like CSS, HTML, you know, those languages. And then we have our libraries for the rest of the things that needs to be processed. Okay, we also have the Android runtime, okay, which is supporting specifically the functionalities that are needed by Android, you know, to support the system. And finally, we have the application framework, which processes and sends application requests to the operating system for process. So how it works, you download an application, okay, the application framework takes a request or response from, takes actually a request from the application, okay, depending on what type of application there is, it uses some of those libraries, you know, to understand the code. And finally, it does system calls to the kernel in order for the hardware to be able to perform those tasks. Okay? Okay. So now once we know the different types, I'm going to move on when we have the operating system implemented. What are some of the things that are some basics on what every operating system should be able to do? Okay. So the first very important thing for an operating system is to, if it generates an error, to always generate a log file with some system data related to that failure. Even sometimes, even not related to the failure. For example, to dump some data about the devices, what space from those devices was used, and those type of system information. This several operating systems should do for debugging, right? If the system crash, the whole system, normally it should generate a crash dump, which is a file with some information about the crash. Okay, many operating systems, they're generating just lines of memory bits, okay, related to the error that happened into the operating system. So then those lines of bits, they can be read from some interpreter and give more information about what happened with the system. Okay. Okay, so I'm not gonna cover too much performance tuning, okay, but this is pretty much how we can use, even as a users, let's say the task manager, or I forgot how it's called on Mac, in order to manipulate processes and to release resources on our device. So when we build operating system, obviously we want to have this type of tool to allow the user to actually free some memory if the user is not a programmer. Okay, this is sometimes a very big issue with operating systems, that they are actually getting slower and slower over time, and normally this is because more and more processes are running in the background when you start them. Okay. And finally, this is the final slide of today, so soon I will let you go. Finally, for every operating system, obviously, we need to have a bootstrap loader, which, do you remember from the last class, what is that doing? Any ideas? Sorry, yeah? Exactly, loads the OS into the memory. Actually, for every chip and every computer, we have a bootstrap loader, okay, which helps us to install the operating system, okay. So this bootstrap loader is normally stored in the read-only memory, so it can never be deleted from your computer, okay. And with it, you can install operating system. Obviously, we need to design the operating system in such a way, right, that the bootstrap loader can have access to it, okay, and can interact with it, okay. And we're going to cover the bootstrap loader and how is that done in some of our next lectures.